Okay, we're going to look at expanding or finding polynomial expansions to approximate binomials that are raised to a rational exponent. First of all, remember raising a binomial to a natural number exponent is the binomial theorem, and so it's summarized here. Take a look. Notice the only difference from what you've seen before and used before is that IB puts a little n at the top left rather than the bottom left. We're used to doing NCR, but IB does n at the top. It means the same thing. Okay, so Isaac Newton generalized the binomial theorem to allow for negative and fractional exponents. Obviously, it's not going to be exactly the same, but it's going to be a polynomial approximation, which will, the more terms you have, the more closely it will approximate it. So let's just look at doing it the old school way, basically. So 1 minus x raised to the negative integer. So let's just think about, we're going to look at 1 minus x raised to the negative 2. We're going to start with 1 minus x to the negative 1. If we remember our geometric series, that converges if absolute value of x is less than 1. And so the expression, remember our first term in this case is 1, our common ratio is x, so the sum of the series is 1 over 1 minus x. So that geometric is the polynomial expansion of 1 over 1 minus x. And so 1 over 1 minus x is the same as 1 minus x raised to the negative 1. Okay, so we've already looked at that last week. So now let's use that to consider 1 minus x to the negative 2. So we're going to show that as a power. So 1 minus x to the negative 2 is the same as 1 minus x to the negative 1 raised to the exponent 2. So now our approximation of 1 minus x to the negative 1 and it says of at least degree 3, so we want to show at least degree 3 terms in each. So it's just a repeated factor. We're doing this the old-fashioned way, distributive property. Okay, so you're going to expand the first term times everything in that bracket. So that'll just be 1 plus x squared plus x cubed. I'm not going to go past x cubed because we're just going to degree 3. Then if I multiply the next term by everything in the second bracket, I'm going to not do it horizontally. I'm going to line up the like terms. So x times 1 is x. So I'm going to put it down there. So this will be a plus here, right? Plus x cubed plus, plus x squared plus x cubed and so on. And then x squared times everything will be x cubed. In blue. Plus, do the same thing over again. X squared plus x cubed. I'm not showing any more terms because they're really irrelevant for a degree 3 polynomial. So I've done those, and then x cubed times everything, that'll just be the first term, which will be x cubed. So collect like terms, 1 plus 2x plus 3x squared plus 4x cubed and so on. And that's our polynomial approximation to degree 3 of 1 minus x to the negative 2. Now, if we look at 1 minus x to the negative 3, again, based on what the work we've just done, we can show it as the product of 1 minus x to the negative 1 times 1 minus x to the negative 2. And so just put the decimal approximations. Of each. It says at least degree 3, so I'm going to show up to degree 3. And then expand out first term times everything. And same, that's going to be 1 plus 2x plus 3x squared plus 4x cubed. Then x times everything. So that's going to be x plus 2x squared plus 3x cubed. Then x squared times everything will be 2x squared, 2x squared plus, x squared. X squared plus 2x cubed, that's everything. And then the last one will be x cubed. Okay, and so I've kind of run out of space, but that's going to equal 1 plus 3x plus 6x squared plus 10x cubed. Okay, so that formula is in your data booklet, and it says use that definition to find the polynomial expansion of the exact same question we just did. Okay, at least degree 3. Is it the same? So what I do is I look, okay, well here we've got 1 plus x raised to the negative 3. So we need a is 1. We need b over a, so that's negative x over 1, which is negative x. And we need n, which is negative 3. So this is going to equal a, which is 1 to the negative 3, which is just 1, right? 1 plus n times negative x plus n. So you'll notice now how we're subtracting from n, it's integers. So they are getting smaller. They're not going down to 1. So it's not shown as a factorial. So that's going to be negative 4 over 2 factorial times negative x squared. And we need to go to degree 3, it says. I think in the data booklet it only shows to the degree 2, or the squared term. I mean, this could be an x squared in here, I guess. But I added an extra one for your notes. Extra term. Okay, so 1 to the negative 3, you can just drop it. It's 1. So we get inside the brackets 1 plus 3x. That's going to be a plus again. And that's going to be 6x squared. Then simplifying, that's going to be plus again. 2 times 5 is 10, x cubed, and so on, which is the same as how we calculated it or determined it before. So really, you don't have to do the long way, which was the previous page. Now you have a formula that you can use. Typically, what I've seen for IB exams is usually the first term is 1, okay, but this works for anything, right? So let's use the same formula to calculate the polynomial expansion with terms up to and including the fourth degree term. Okay, so this says including the fourth degree, that's at least degree 3. So you can stop and in this case and not put dot 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 afterwards. We just want the fourth degree term included. So here our a is 1, our b is negative 2x over 1, which is negative 2. Our n is negative 4. Oops. Oops. We're off? Usually, actually, they'll be given to you. Right. But here, this would be, that ratio has to be, so negative 2x absolute value has to be less than 1. So x would have to be between 1/2 and negative 1/2. Okay, so this will be a positive 2, that's 10. No, sorry. 20 over 2 is 10 times 4 is 40. 20 times 8 is 160. Oh, it said fourth degree term, didn't it? Oh. Okay, so let me just move this down. There's your polynomial of degree 4 that approximates 1 minus 2x to the negative 4. Okay, take a look at the next one. Same thing, 1 plus 3x to the negative 5. So your first term is 1, b, that should have been b over a. b over a is 3x, n is negative 5. Five on that one. Um, 9:45. Okay. All right, so turn over to the next page. This now has rationals that are fractions. Okay, so express the following terms up to and including the third degree term. So I would show this as a power, so that would be an exponent of -1/2. So now your a value is 1, b over a is -3x, n is -1/2. 1 to the -1/2 is still 1, which is going to be nice. But now we're going to have fractions. And you're going to subtract 1 from, keep subtracting 1 from each n value. And we're just going to the third degree term here. So you can use your calculator if you need to, but that's going to be 9 times, that's going to be 27 over 8x squared. And then that's going to be a positive again. So that 3 divides out. 27 times 5, 135 over 16 x cubed. And so in this, so we've done a polynomial expansion with a rational exponent, -1/2. In the next part, and this is terminology that's often used on IB exams, they'll get you to do part 1, and then they'll say hence or otherwise. So that really means their hint is use what you just did. The otherwise means you can come up with some other idea of how you want to do it, but the first part is your big hint. Use it, right? So hence or otherwise means they will take other work, but hence means take a look at the previous part and see if it will help you. So here, take a look. The denominator is the same in both. So this is a polynomial. It's an easy binomial, right? It's not an approximation. It is itself, right? If we expand that out, it is the polynomial. It's not even an approximation. So we could show this as 3 plus x squared times 1 minus 3x to the -1/2. Well, we've already found the polynomial that approximates 1 minus 3x to the -1/2. So let's multiply those together, right? So this, when I expand out 3 plus x, I get 9 plus 6x plus x squared. It's already a polynomial. And then from above, that's 1 plus 3 over 2x plus 27 over 8x squared plus 135 over 16x cubed. You would check, like if it wanted at least, or you want to just check and make sure you've gone high enough for the degree terms. For example, if these both had x's in it to start, then there's no way we wouldn't really need the x cubed term in the expansion, because these, when we expand out, would be all higher than degree 3. But we do need up to at least degree 3 for each part in this case. So now when you expand out this first term times everything, that's 9 times 20, 243. Okay, then same as what I did before, I kind of line them up so it's easier to collect like terms. So that's actually going to be what? 9x plus, oh, sorry, not 9x, 6x plus 9x squared plus 81 over 4 x cubed. And I don't even need the degree 4 term after that. Okay, that's it because there's just the 3 terms there. So when I collect like terms, I get 9 plus 39 over 2x, 9, 10, that's 80, plus 243 is what, 323 over 8x squared, I think, plus, you can use your calculator if you want. What's that going to be? 1215. 4 times that is 324. 8 times that is 24. 13, 6, 5, 1. So that's the polynomial approximation of that expression. So 2 parts to it. Okay, so get used to using what's in your data booklet. That's what will be on your test, on your IB exam. Okay, there are, if you research, you can look at different versions of it. That's what I had previous notes, what the version is if it was a negative, okay, what the version is if it's a fraction, and so this is combined and it's in the data booklet, so I want you to get used to using that. No sense learning more formulas when it's all together in one, okay? So that's the last lesson. I do have a few review review questions to hand out that you can work on as well today or tomorrow. There are a couple as well posted in D2L, okay, with solutions, so you can take a look at those.